Good morning, one and all. Hi, I am here to explain. Hi, I'm Vishal. I'm from Triple E branch. I'm from third year. So I'm here to explain about short circuit protection circuits for silicon carbide powered transistors. Yes, we all know about short circuit protection circuits, right? And silicon carbide and transistors like BJT transistors and all those etc we all know about it, right? Yes. So here, silicon carbide SiC transistors have undergone a great development over the past few years, and their level of maturity is now sufficient for product development of converters for various applications, ranging from motor drives from different kinds of vehicles to various industrial applications, high temperature operation, high frequency applications, and renewable energy generation. This in this interest motivates research efforts towards application reliability. The currently existing SiC power devices are junction field effect transistors JFETs and metal oxide semiconductor field effect transistors MOSFET, which are unipolar and voltage controlled, and the bipolar junction transistor BJT, which is bipolar and current controlled. However, it behaves as a unipolar device that both with respect to conduction and switching properties. So, short circuit behavior of SiC power devices. There are two types of short circuit faults. A fault occurring during the transistor turn on transient is referred to as hard switching fault HSF, and a fault occurring during on state conditions is referred to as fault under load FUL. A complete analysis of these two types of faults has been given in during both short circuit types. The current rises rapidly and the device saturates. As previously investigated in for SiC MOSFETs, both fault types can be detected by means of the desaturation technique. However, the detection delay times are higher for HSF than for FUL. Consequently, only the HSF will be studied in the present paper in order to limit the scope of investigation. So we can see here the diagram with voltage with DC supply, and series with capacitor and inductor, and then here we can see the diodes VCC and VSS IC driver DUT and inductance and resistor. There are two resistors, two diodes, and one VCC and VSS IC driver. So yeah, short circuit behavior of voltage controlled SiC power semiconductors. So first, two different SiC MOSFETs C2M002512 from CREE and SCT2080KE from ROHM, and one SiC normally on JFET UJN1205K from USCI are investigated. The short circuit pulses of 500 ns for the MOSFETs and 250 ns for the JFET. The main difference between the two MOSFET are the chip size and chip thickness. The driver output stage is powered by a positive voltage source of 24 volt and a negative power source of minus 5 volt. The external gate resistance is 20 ohms for both turn on and turn off. This value guarantees low oscillations at turn on and turn off, while the switching times remain below 40 ns. In the case of the Normally on SiC JFET, the driver was powered by a negative voltage source of minus 30 volt and the gate resistor was replaced by a DRC network. So here we can see in this table, so short circuit behavior of voltage control devices. In this table we can see SiC DUTS, peak current over voltage turn off time. So here we can see the supplies in the C2M0025120D. Here 500 amperes, 200 volts over voltage and turn off time was 320 nanoseconds. In SCT 2080KE, in current was peak current was 300 amperes and over voltage was 150 volts and the turn off time was 140 nanoseconds. And then and then in UJN1205K, peak current was 120 amperes, over voltage was 200 volts and turn off time was 40 nanoseconds. So short circuit behavior of current controlled SiC power semiconductors. So in the present subsection, two devices rated at 1200 volts per 50 amperes from two different suppliers are analyzed. Those are the SiC BJT from Fairchild, FSIC BH017A120, and the super junction transistor SJT from Genesic Gen SiC GA50JT12247. SJTs are super high current gain SiC BJTs. For simplicity, this device will be regarded as a BJT in this paper, the SiC BJTs. So here we can see the graphs of in the first figure. So short-circuited CRAE MOSFET resistance was 20 ohms, measured gate to source voltage yellow line 50 volt DIV, drain to source voltage purple line 200 volts DIV, and the drain current pink line 200 DIV, time base 200 nanoseconds DIV. So here first one in the voltage GS and VDS, and the current was we can see in the initial stage it was constant and then it is going upwards and then it is coming downwards. So here in the third figure we can see short circuited uh, home MOSFET 20 amperes, time base 200 nanoseconds, yellow line 50, and the drain source purple line is 200 volt DIV. So temperature distribution in the die during a short circuit. The present section discusses the time evaluation of the temperature distribution in the chip during a short circuit event. The device investigated here is the SiC MOSFET, as its oxide layer may be sensitive to heat dissipation in the die. The gate oxide of SiC MOSFETs is thinner than one of SiC MOSFETs. It is thus exposed to a higher electric field for a given gate bias. The high electric field and current density to which the oxide layer is exposed during short circuit conditions may increase the tunneling effect known as the main degradation mechanism of the oxide layer of SiC power MOSFETs. The failure modes of SiC MOSFETs when subjected to longer short circuits has been investigated in the presence of a gate leakage current after a few microseconds of short circuit is observed, which is not the case of SI devices. SiC MOSFETs showed low robustness to cumulative short circuits for longer short circuit durations. The failure mode translates in a short circuit between gate and source for some devices, and other devices additionally have shorted drain and source. with the knowledge of the behavior of various SiC devices under short circuit conditions acquired. So several design rules toward a rugged short circuit detection can be derived. A driver with an integrated SCP can be designed based on those rules. While most driver manufacturers are targeting SiC MOSFETs, the proposed solution can also be applied to the SiC types. So, in the present publication, the slower turn-off is achieved for the SiC MOSFET with asymmetrical gate resistors to for turn on and turn off. As illustrated, we can see on-state voltage drop of the device during a short circuit fault is much higher than during normal operation. As emphasized above, a fast detection not only reduces the current level, uh, additionally, the voltage overshoot at turn-off is limited. The proposed implementation has the following targets. Here we can see in this diagram, enable in M3 conventional driver R1, diode 1, R2, R3, R4, M1, error, enable, etc. The peak fault current during a short circuit connection is inherently limited for SiC BJTs. For similar short circuit duration, SiC JFET and MOSFET, nevertheless, there is no need to wait for more than a few times the duration of a normal turn on in order to turn off the short circuit. The RC filters are calibrated in order to achieve a short circuit detection within 380 nanoseconds. The SIC driver is the one used in section 2 without modifications combined with the short circuit detection. Short circuit protection of SiC power MOSFETs. So with here SCP driver for SiC MOSFET should be designed carefully for the reasons mentioned in sections 2 and 3. Reduce it to the minimum value, allowing a small margin to avoid false triggering. The turn-off is slowed down by means of asymmetrical gate resistors. As for the SiC BJT, a high noise immunity is also required. In this realization, there is no real difference between during a SiC discrete power device and SiC power module. Expect on how to tune the delays of detection circuit is to match those waveform and turn on transient of specific application. Special care has to be taken to this aspect if the load exhibits a significant capacitive currents at a turn on. As for instance, a motor winding, if the detection delay is too short, even normal transients may erroneously be detected as short circuits. Thank you so much.